Welcome everyone for the AI against oil spills final presentation. We organized this challenge together with Rijkswaterstaat, and I want to say big thank you to Rijkswaterstaat for sharing the data with us and also organizing this challenge. It's been a very cool process to go through. We've learned a lot, and I think we made some very nice progress. So I'm very happy to be sharing the results with you guys. Furthermore, a big thank you to Port of Rotterdam, Port of Antwerp, and Shift and Co1 for helping us out with sharing data as well as expertise and also helping us with labeling some data. For today, we have a presentation about the final results of the challenge. I will do the introduction, then the team will present on oil segmentation and classification. We'll finish up with some recommendations and hopefully go into a discussion. And I've left some time in the end for some final words by Maurice from Rijkswaterstaat. For everyone who doesn't know us yet, we are Fruit Punch, the global AI for good community, and we started this community because we believe that to solve humanity's greatest challenges, we need to educate AI engineers at scale with an ethical and sustainable mindset. We do this by organizing AI for good challenges in all of the spaces that relate towards the sustainable development goals. So you can think of biodiversity, climate change, AI for health, all these spaces we organize AI for good challenges in, which you can partake in and learn about AI. For this particular challenge, we have looked into the problem in how we can improve oil spill cleanup. As you can see here, oil spills can be very bad for the environment. They have a tremendous effect on water life. But as you see in these images, these are sea spills. But what people often don't realize is that most of the oil spills actually happen inland, so in inland waterways. You can think of sinking ships or old boats with leaking tanks. Those are all oil spills on a way smaller scale, but also need cleanup. Well, for those smaller oil spills, we have organizations like Rijkswaterstaat and especially the oil cleanup team, response team, who come to those locations expertise to clean up this oil. How they do that is first they fly over the area to locate where all the oil has gone and how big the surface area of oil is. And using this drone imagery, they can calculate how much cleanup or how to approach their cleanup response. To help them with this task, we aimed to use AI to help the drones fly and help to analyze how much oil there is in the water. So the main goal of this challenge was utilize drone captured images as input data for an oil volume estimation tool, thereby facilitating the calculation and assessment of oil quantities. We split up this challenge in a couple of smaller goals, which initially we formed separate teams for to tackle each of these sub-goals. Later in the challenge, we merged the goals as we saw that a lot of the problems and a lot of the hurdles that people or both teams approached were very similar, and we've benefited more from combining the teams. But the sub-goals we tried to solve was training a segmentation model to segment the oil out of the water. Then the second team aimed to train a classifier to see which segmentations of oil, which thicknesses they were. And the last team, or the last sub-goal was to combine the segmentation and classification to come out at an actual estimation of oil volume. Now, we worked for 10 weeks with 2 groups and eventually with 12 AI for good engineers and a combined effort of 1,000+ hours of engineering work. And I have a very good team with me today who's going to present their results. So the first person I'd like to introduce is Sugan. He will be talking a bit more about the data we had at hand, as well as the pre-processing we did and data cleaning. I can stop sharing right here. Yeah.
So hi, I'm Sugan. Thanks for the introduction, Dorian. I'll be one of the few speakers today. So just before to get started, we wanted to first of all kind of highlight what the focus of the project would be. So of course, here is kind of the procedure of the contingency, kind of the plan when an oil spill is then spotted. First, of course, is reported. And then it is our understanding that Rijkswaterstaat sends a drone team that goes to the location and then takes pictures in various angles and various altitudes that we've seen, of course, as well. And these drone images are then perhaps could be loaded to a tool that estimates volume of the oil spill. And that part was the focus of this project, of course, to segment the oil, to classify the oil type, to lead towards the volume of the oil spill, so that it can help Rijkswaterstaat decide what cleanup strategy should be deployed. Next, please. So of course, in such a volume estimation tool, we would need 3 steps that we kind of highlighted and outlined beforehand. One would be to combine different images. What does this mean? It means that drones fly over an area taking multiple images, but to have a clear view of the entire spill, we would need to patch these images together and discard duplicate pixels. And the other bit would be then identify pixels that actually have the oil spills. That just means segmentation of the oil. And after that, we would then have to convert this pixel and to classify which pixel belongs to which type of the oil, so that we can use the so that we can tell which how much of the oil spill uh is then happened, because depending on the class, on the type of the oil spill, we know how much volume, how much liter per square kilometer is the oil spill. Next, please. Of course, I can already kick off actually by giving you a bit of a spoiler or a disclaimer about the findings, the conclusions that we had before we actually go into what we've done to actually achieve these results. So first thing that we found is data quality is really important, just as many other data science projects. So we really would benefit from, of course, Rijkswaterstaat would really benefit from, if they were to take upon this approach and develop it further, to have consistent labeling. So annotation should be consistent. And of course, also consistent data gathering. What does this mean? It means that there should be a standardized manner to take pictures and to take images in such a way that we could use an estimation tool that could be applied to multiple images at multiple different sites. What we also found is that binary oil segmentation, by that I mean segmenting just oil versus not oil, that seems possible. Now I don't mean classifying different types of oil. I just mean spotting the oil. That seems pretty reasonably good, but maybe they're not good enough in practice. And I think I would like to also maybe this is also purpose of the presentation, to present the results that we have and to see how fitting this is, how good this is in practice, and what's the potential here. And finally, to make this practically applicable, we would of course, need to gather high quality, diverse set of data that's related with what I already mentioned in the first point. But B, we would also benefit from having a clear definition of what is a good model, what is a good solution. In the end, what is the goal? Is the goal really to estimate the volume as much as possible, or is it the goal to really know what cleaning strategy to choose and to deploy as soon as possible? So those things, I think, could also be defined more clearly in order to, let's say, maximize the potential that we found here. Next, please. So I would quickly start over. Of course, to get to those findings, we need to train a model and we need other procedures, but we start with, of course, the model, of course, the data part. And I would really briefly mention what we've done to reach to get the data that we worked with. So of course, we were provided nicely from Rijkswaterstaat more than 500 images from different locations in the Netherlands, but also we had annotated images from Port of Antwerp, Rotterdam, and also Shift. We started off from that. And next, please. But we had to do a lot of pre-processing. And I would now go through step by step what sort of pre-processing steps that we've done. It entailed both cleaning, but also enrichment. And in the end, leading up to a nice train validation test split that we used to train our model. So first of all, we had to clean a lot of data set, a lot of images. What does this mean? We had to actually discard a lot of images because the annotation quality wasn't that great. Now, this, of course, ties in back to one of the conclusions that I already told you about the quality of annotation. So this was also briefly touched upon during the midterm, so I will not go really deeply into it. But if you see on the left-hand side here, you see this nice blurry bit, but it is very, yeah, I would say pretty difficult, but not only difficult, but also pretty incorrect to say that some of this is metallic and discontinuous. I would say that they're mostly sheen. Next, please. Also, here is an example on the left top side, which is labeled as discontinuous true color. In the end, it looks like, and I think it turns out that it's just a sun ray beam that's kind of being shined upon here. So not really a bright moment for the annotation crew, but it is something that to be worked on, of course, I think for the future. So these kind of images were discarded from the dataset first of all. Another problem was that although the annotation quality might be great, there were images that some spill was just unclear, just not really visible. So for instance, if you see here on the left-hand side on the image itself, it would be really difficult for me to tell whether how much of an oil spill is, and a lot of times the edge is very unclear as to define the oil spill. I think that during the midterm, we've also been told that that finding and really detecting and segmenting the Sheen class especially is a difficult task also for the operators that work together right now doing this manually. So I think in that case, I could also imagine that these images, if they get in here to the model, it could be quite a confusing aspect, confusing contribution to the model. So we also discarded quite a lot of images where the spill was unclear. Well, next, please. Similar story here, where the edge is very difficult to see. I think we can move on. So we've conducted quite a significant amount of cleaning, meaning discarding a lot of images that would not really contribute to the model. Another bit that we did was to discover additional data sources that might be available. One trouble that we had was that a lot of literature have really focused on using satellite images, satellite-based remote sensing methods. So not only images, but also, I believe, radio waves methods, infrared image, for instance. So those were predominantly the methods being used in the literature. So it was quite difficult to find extra data sets, extra sources, but we managed to find a source that used some of these drone images that they found online. So these researchers just found publicly available drone images and they annotated them themselves. In the end, they provided 1,000 images, but we can move on. But among which actually we also had to clean up a lot of them, because if you see here, for instance, on the right top, that's like an oil rig image, and I would say for the data set of Rijkswaterstaat and for the purpose of Rijkswaterstaat, this is not very relevant. So therefore, we ended up with the next slide, which is only about 47 images that we deemed quite relevant for the model, for the use case of Rijkswaterstaat. So that was also what we did. So we removed a lot of images, but enriched them also. And finally, what we did in the next slide is we enriched it further by applying an earlier model. So during the process of cleaning and such, we were always trying to make our model better. We were always training some models. And one of the models that we had performed reasonably okay. So we actually applied to all of the annotated images, all of the unannotated images that we had. For instance, one provided from from Antwerp, Rotterdam, but also from the recent Arnhem spill where the annotation was unavailable. We applied the model there, and then of course the quality wasn't the greatest, so we further annotated them manually ourselves to get some more quality annotation and quality images. And all of this enrichment we really did because I think this point will be touched upon later on as well, but because the number of images is really great, of course. That's one parameter that's great, but also the variability of the images is important. So if you take 1,000 images from one site, that may not be as valuable as, let's say, 100 images from different sites. So we were really trying to aim for a nice various sources of data where different variability of oil spills can be visible and can be present in the model. Next, please. So in the end, we came up together to a total of 352 images, where we also removed some duplicates in the data set. And that's how we worked with by splitting the 352 by train, validation, and test. In the next slide, by taking into account of the information regarding the location of the spill and such. Sorry, I already covered this bit about the Arnhem spell. Arnhem spill, sorry, I should say. Um, Actually, for the Arnhem spill, I have forgotten to mention something, and that is that not only we used the we didn't actually use an earlier model there, but we actually just manually annotated ourselves. Just a small caveat here that I just did not want to miss uncorrected. If we move on now. So finally, we split it those total of 352 images into this split. And then we were training different models on this data set so that we could compare the performance of the models, let's say. And we really made sure that, for instance, data leakage doesn't happen. What does that mean? It means that when an oil spill from, for instance, Zeeland happened, and if that's in the train set, the images from the same site would not end up in the test set, because that would mean that there's a data leakage, so the model is unfairly receiving advantages in order to detect the oil. So given this pre-processing of the data, we have then trained some models. From here onwards, I think Gerson is going to take over and talk about the model being trained and present the results from then.
Just a quick question about the Arnhem spill. You said you annotated it yourself, but just annotation between oil, non-oil, I guess.
Correct. Yes.
Okay. Yeah. Clear.
Nice.
Yeah, this works. Cool. Thanks. So I'm Gerson, and I will be presenting the binary segmentation models. So for binary segmentation, we use two classes, so the oil class and the background class. And the oil class consists about 20% of the pixels, and the background class was about 80% of the pixels. And we tried different models. We tried Unet, we tried an improved version of Unet, which is Unet++. We also tried the segment anything model, SAM, and also the well-known YOLO model. But from these models, Unet++ worked the best. So that's what I will be presenting. For training and evaluation, we used the following things. So for training, we used dice rolls. To evaluate the model, we mainly used intersection over union. And yeah, that's just a score. Simply said, it's a score between 0 and 1, and 0 is like the worst score, and 1 is the best score. We also used a confusion matrix, and that is to dive a bit deeper into what kind of errors the model makes. And lastly, we also did some qualitative analysis, and that is to get like a good feeling about what kind of predictions the model makes. So the Unet++ model, we trained the Unet++ with an efficient net B1 as a backbone. And I won't go too much into detail about how these models work. But Unet++ is like a well-performing model that comes from the medical image segmentation domain. And efficient net B1 is, as the name suggests, like a very efficient model that is like a state-of-the-art when you look at like the number of parameters it has compared to its performance. And for this model, we got the following results. So we got an intersection over union for the background of 0.87. So this is like a very high score for the background. And then for the oil class, we actually get like a much lower score, so 0.47. And the mean intersection over union was 0.67. But to dive a little bit deeper into the results, we can look at the confusion matrix. And this tells like a more complete story. So what we can see is that the model seems to perform pretty well, I would say. So usually when you look at the top left corner, you can see that the model is able to find out what the background is. And in the bottom right corner, you can see that it also usually picks up on the oil, but it also makes a lot of mistakes in a form that it predicts background, but it's actually oil. So that you can see at the bottom left corner. And when you look at the qualitative results, so if you look at the predictions, you get the same story. So for this part, it's important to look at the second column and the third column. So in the second column, you see like the true mask, and in the third column, you see the prediction of the model. And what you can see, for example, in the first row is that there's like some oil in the middle of the image, which the model doesn't pick up. And you can see that happen more often. So in the middle row, you see the same thing. There's like a small line of oil in the middle of the image, and the model doesn't seem to pick that up. Another error that the model makes is that it often fails to fill in the details. So that can be seen in like the bottom row. In that you can see that the oil is supposed to be a bit complex. It has like there are like parts where there is water inside the oil, but the model itself just predicts like one blob of oil. So I think these are like the main two kind of errors that the model makes. And yeah, now the question becomes, okay, is this model good enough to work in practice, or do we need like a better model to make this useful? But I think that's also like a question for Rijkswaterstaat. Like, when is a model good enough, and is this something workable or not? And then I'll hand over the presentation to Saradi, who will be talking about the multi-class segmentation.
All right. Thank you, Kherson. Now I will be presenting our team's work on multi-class segmentation. So at the onset, what we set out to do was to develop a multi-class classification problem to classify the various oil spills into different classes of rainbow, sheen, metallic, etc. But as soon as we began, we ran into a problem, which is depicted here, which is that the percentage of water and not water classes was really high. And this is how the data was represented: water, not water. Not water meaning land, ships, boats, etc. And what was the crux of what we set to do? The oil classes, they were underrepresented. There was not enough data available. What would this lead to if we trained a model with such an imbalanced data set? Well, the model would be overfit with respect to the water and not water classes, and underfit with respect to the oil classes, which would eventually lead into many problems. And we had to somehow mitigate this. So what did we start with? How did we reframe our problem? We first then split it into simple classes, a simpler multi-class problem, where we combined the oil classes and made it decided to train an algorithm to segment into three classes, which is oil, water, and land. So, which is reasonably not as imbalanced as the previous one. This ensures more even class distribution. Why did we do that? So the rationale was that if we have good results with this approach, we can then proceed with the harder problem of classifying a given oil spill into its subclasses. So what did we do? We applied a patching algorithm. What is meant by patching? Well, you can see that on the left-hand side, there's an image. We split this image into different patches, and so into 1024 into 1024 patch. What happened here was that we then deleted those patches which did not have an oil spill in them. So this ensures that our data has more of oil spills and it does not maybe be biased towards a few classes. And then we augmented this data set for the patching. We augmented the patches. After this was done, we ran a segmentation algorithm, Unet++, with MobileNet v3 backbone. And our mean intersection over unions was 0.6. And as you can see from the confusion matrix, especially with respect to the misclassifications of water as oil and oil as water, they are little bluer, which is not something that is desirable from a classification perspective. And this only means that the performance is not great, so we cannot generalize it, or we cannot extend it to a harder problem. And the model basically struggles to distinguish between oil and water. Qualitatively speaking, this is the image of one such oil spill. You can see the actual image, and then these are the masks. Purple is for water, red is for the spill, and green is for the land. And what happens when you run the algorithm on that is that for the predicted masks, we can see that water is probably recognized correctly, the land is, but when it comes to detection of oil spills, the model is mostly confused. If you can see the one in the middle, the top middle image, it's not fully recognizing it as an oil spill, which means the model is getting confused between oil and water. And this is a bit of a bummer that way, but unfortunately, but this is what it is. And yeah, so I end here, and I would like to now hand over to Rafael.
Yes, I'll take over. So if we look at the zoom out again, so we have looked at the model. If we zoom out again and think about these separate drone images, then we need to combine those into a single image. And there is open source software and algorithms that are able to do such stitching if there's enough reference points in the data, and if there's enough overlap between the pictures. And we attempted to do the stitching using the RNM photo run, but at this point there was not yet enough reference points within the image and not enough overlap for that automatic stitching to work. And then a different way to still get to the stitching is just using the GPS information of the drone. And if the drone doesn't move its angle or direction, then you have an intermediate solution, which could also work, but then you lose some fidelity. So we would recommend that the drone image makes a lot of overlapping images, and preferably with clear reference points. So like having the shore 30% or more in the field of view. That would be probably the best idea. Then moving on to going from pixels to some sort of area or volume estimation. Each drone image has metadata included, That's GPS information, which also includes its altitude. And also, since the drone used by Rijkswaterstaat has two cameras, either a telecamera or a wide lens camera, the photo image always also contains which camera was used. So using this information and knowing the specifications of the drone, in this case for the tele-lens, knowing that the field of view of this camera is 15 degrees and that the images created are 4,000 pixels wide, we can use Pythagoras theorem to go from the altitude in the field of view to the radius covered by the drone camera. And as such, we determined that each pixel in the images at this altitude, at a certain altitude, so here it was 114 meters, is 1.56 centimeters per pixel. And we want to know, like, because this is a formula, so you can apply it to any drone picture you make, and then we want to know, like, how accurate is this information, because this field of view could be slightly off, the GPS altitude could be slightly off. So
Can I make a remark about that?
yes,
Because the attitude is in this case you got it from above sea level, but it was in Arnhem, and Arnhem is already around, at the top of my head, 30 meters above sea level. So the drone actually is not really 140 meters above the ground.
well, that's good to know. Yeah,
It's closer to the ground.
so with
That's
the so I also include this standard deviation of 0.12, and that was like taking into account a altitude variation of 5 meters and a field of view uncertainty of 1 degree, but then both the altitudes can be different. Can be increased, so you can change the formula.
I think somewhere in the metadata is also the attitude from its starting position. Then you still don't have the actual attitude from the position where it makes the picture, but it's more of a closer attitude than the mean sea level in this case.
Nice. Well, that can also be used then. So for the calibration, just refer to looking at a certain picture of the Arnhem oil spill, taking reference points within that image. So for example, the two lantern posts you see in the left below were 1500 pixels apart. And then if you go to the Google Maps location of this image, you can find the same lantern posts and see that they're 24 meters apart. And then you can sort of calibrate this centimeters per pixel. And you can see, like, if I do it this way, then get to a slightly higher number, might be impacted because of this sea level thing. But still, it was like within 10% of the other number. Overshoot. So if you increase the altitude, it might overshoot in the other direction. But I think it's still quite reasonable. So you introduce maybe a 10% error in your in this conversion, but it is possible. So that's nice. Putting it all together for a single image, not a stitched image. If we take an image that's filmed from above with a 90-degree angle, taking the altitude data from the image, which now we know is slightly incorrect, but more or less okay. When we feed this image through the model, we get the blue area as being oil. And then using this pixels to centimeters conversion, we get to this 141 square meters of oil. And it's important to note this is just like a small part of the oil spill. It extends on further to the left. This is illustrative. And what's even more illustrative, I think, is going from the area to the volume. So here, if we assume it's like half sheen, half rainbow, maybe full rainbow is a better approximation here. But then you get to volumes that are less than a liter of oil, which is quite interesting because the visual impact is quite big. but then the actual amount of oil can be quite small. Of course, it needs to be this image like the oil spill extends way further out. So, but this is the full demonstration of going from the image to a volume estimate with the model that the team trained. And I'll finish with the takeaway message, which is that oil spills can be roughly segmented. With the current data, different oil types cannot be distinguished. Converting pixels to square meters introduces some uncertainty, but is possible. And then recommendations would be that for this oil type distinction, more and especially more consistent data is required. And then keep in mind that for each oil spill, there's maybe 5-ish uncorrelated data points, however many pictures we take from different angles. Then to tackle the imbalance between oil, water, data scientists can apply all kinds of tricks, which is what our team did. So we did undersampling of the water and land, oversampling of the oil, applied patching techniques and augmented the data. And then for the drone team, it's quite essential to be able to go to volumes for the drone to film down, to not use digital zoom, to use a fixed altitude, and which altitude is best for the model. That's something that can be determined empirically by doing like test runs at say 100 meters, 50 meters, 200 meters, and then feed it through the model. And if the goal is to gather more data from a single oil spill site, one could think of taking a series of drone photos at the same altitude, but say 20 minutes apart, such that the water and the oil moved, and then you have like somewhat more uncorrelated data points. And finally, for this whole thing to work, the GPS information is quite crucial. So it's important not to take screenshots or compress or do something to the images such that the information is lost, which sometimes happened with the data we had. And that's it for now. So I think we can go to the Q&A.
All right, thanks, Rafael, Charlie, Gerson. So again, great presentation. Really nice how you guys pulled this off in the end. Yeah, still a lot left to wish for, it seems, and which was also expected. But I think in the last couple of weeks we made some great progress. But yeah, I'd like to open the floor for questions. Maybe Maurice, what are you thinking?
Yeah, still one question about the thing Rafael was explaining. The stitching was only being done with the pictures or the photos being made straight down, right? Not with an angle.
Yeah.
Correct? Yeah, okay. Yeah.
Yeah, so the thing with the angle is from the image metadata, I could not retrieve the angle of the camera.
Okay.
So that means that if the angle is not known, then it's not really possible to get to some sort of area.
And the stitching program is also not able to cope with that, I guess.
I tried different stitching programs, but it seemed to, I guess because of large portion of water, that's like hard to find reference points. So yeah.
I can imagine. Yeah. Well, my first thoughts are well, actually impressed with the data set that you were provided. As we discussed a couple of weeks ago, the current data set is not really the best data set for this stage, I guess. I wrote down a couple of things. Labeling is crucial, and I think we underestimated that at the beginning. If there is any other program or is there, when there's a next step, maybe we can invite you guys to do the labeling now, because I guess that you became sort of labeling experts now. You did some labeling yourself. We don't have to explain to you guys anymore what the difference is between sheen, metallic, and the rainbow. So I think you learned a lot. And for me, I'm happy with this outcome. It can bring us further now from now on. And looking at the stage where we are right now, at this point we are manually flying the drone, and we just detect and we see where the oil spill is. In the near future, I hope we have an AI running on the drone itself. The drone is operating automatically as well, and flying fixed patterns or whatsoever, and the AI and the drone are actually discussing and combining the data into a solution, and maybe the AI is backseat driving the drone, and then you have to now apply a fixed pattern over that location, because I think there is oil over there. So that there is a difference between detection and eventually the classification AI, and that they are on the go, are communicating with each other. That's hopefully possible at some point. So I think this is definitely helping us. Yeah. So and there was a question about what do you prefer, overestimation or underestimation? At this stage, I would say, but that's my personal opinion, I would like overestimation instead of underestimation. But looking at the details at this point, I'm actually already quite impressed that at least this outcome, or this AI, how do you call it, model is already able to detect the oil in the different spots. It's not always the easiest data, or it's hampered by a crane or sunlight or decay. So it already gives us a good impression where the oil exactly already is at this point. So yeah, the first thoughts that I wrote down. It is a solution, but we still have some challenges left.
Yeah, no, definitely. There is a way to go, but there is definitely like going from the final opinion, I feel like it's definitely possible. With the right data, with the right labels. We are still also within our recommendation part in the report. We'll also write down a bit more detailed how we label the data eventually. There are some proper tools out there that help you labeling quite rapidly and also make it, at least for experts, a lot more doable to go through lots of images in a shorter period of time. So I think that's also the main problem starting with this challenge, is we went through a lot of images, but not with experts. And therefore we had to discard a lot of the labels that we had and only stick with the ones that were definitely of good quality. But as you would, if you would label it with some expertise, then yeah, we will recommend some tools that will make your job a lot easier, and will also make it possible to, for example, do, I don't know, 2,000, 3,000 images in a day or two. That's definitely with maybe 1 or 2 people who know about their stuff.
I have one more question for the team. So I know that especially in the start of the challenge, you really set out to also segment the different classes. And this is also when you ran into a lot of these data quality issues. I am already very impressed indeed with the accuracy of the oil segmentation, because in the end you had like 200 images. We run a lot of these challenges with segmentation labels, with definitely more clear segmentable objects. And there we are working with like 5,000 images, and we also run into some accuracy and data cleaning problems there. So the fact that you got results with an MAP above 0.6 with so few images, which is also visually rather unclear compared to like a bear in front of a tree, it's definitely very impressive that you got this far. From your research you did in the beginning, from segmenting the different types of oil, I understood that there were a few of the classes just basically too underrepresented, like true oil, etc. Do you feel like with, let's say, 4,000 images, would it be possible to accurately segment sheen from rainbow, which I understood were the most relevant classes for Rijkswaterstaat?
Well, sheen is not the most relevant class because it's so thin.
Exactly.
Yeah.
A metallic, well, a true color, of course, is the thickest. Then you have metallic, and then rainbow, and then sheen.
Yeah,
Definitely.
metallic rainbow indeed. Because true color obviously is important. However, it's super underrepresented in the data set. So, okay, in that case, indeed, I mean rainbow and metallic. Would that be possible with about, let's say, 4,000 images to accurately segment those two, based on your findings, early findings?
Yeah, I would say in this case that it depends on if these images are like very diverse or not. Like, are they all from the same oil spill, or are they from different oil spills? I think that also makes like a big difference.
Yeah, so let's say 100 images per oil spill. So in this case, you would have 400 different spills dealing with.
Yeah, that would work.
400. I'm mathing wrong. It's
40, yeah.
40 different spills with 100 images each.
Yeah, like intuitively, I would say that would be enough, but you never know with these kind of things until you try it out. But I would be hopeful that it would work.
Okay, good to know. Lawrence, I don't know, I saw you might want to comment as well.
Yeah, I think because we did achieve pretty good results on a multi-class problem, which was in our case only oil, water, and land. But I think it could be easily expanded to multiple oil classes with similar results if we increase the data size, especially for the underrepresented classes. So I think it should be quite doable with that amount of data you're talking about.
Okay. And then also Rijkswaterstaat has a number to strive for where it is likely to work.
Yeah, we aim for 0, of course, but yeah.
Yeah.
But
So-
again, in the past, we just flew and we decided we defined the boundaries, and that was it. That's the main focus point. That's the thickest layers over there, and that's it. It was not in our head yet that we had to teach AI in the future.
And one follow-up question, actually. Because we had quite a decent data set from Rijkswaterstaat side. We only had like part of it labeled because the labeling is also very labor intensive. I think we had over 3,000 different images of about, also again, at least 50 different spills. But indeed not taken in a same altitude type of manner. But again, let's say that this full data set of 3,000 images, 50 different spills, would be labeled very accurately. So you're still dealing with the problem that there's varying altitudes, etc. What's your hunch on that? Like, could that work? And this also would also mean for Rijkswaterstaat, of course, that there is still significant value in the existing data set without going to fixed flying patterns.
I think it's hard to say because some of the images, I think as Zogun also showed during the presentation, are like the images themselves are like hard to label. So I think even experts may not agree on where the exact oil spill is in those cases. So I think a lot of images, the images themselves are not of the right quality.
Mm-hmm.
Yeah,
and at this point, when we have that situation, we lower the drone or we change the angle, and you immediately, determine what kind of spot, what oil we are looking at, and that's not possible in the current data set, of course.
No.
Yeah, indeed. So I think that really helps when you like flying the drone with that you have it in the back of your head. Okay, we also try to teach AI this. So like, how would we get like high quality data?
Yeah, so based on this, you would recommend gathering new data instead of spending resources in labeling the old data.
Yeah, I think that would probably be a better investment of time.
Okay, I guess that's good to know.
Yeah, I mean, I think that like it's possible, for instance, like rainbow gets picked up pretty easily, I think, by the model. It feels like. So maybe that could be like given, let's say if we use the images that we have and we have like really good annotations, really good labels, then I do think that, yeah, perhaps there could be a strategy if we really only want to focus on rainbow and metallic, then I think perhaps they could be somehow targeted separately rather than going for them together. Maybe it would be a question of how to approach it.
One more tip there for you guys. There are many ways. If you would find a way to inexpensively label the data, what is a very common way of solving this issue is having every image labeled by 2 or 3 different non-experts, let's say in this case. And then there are various algorithms and metrics for which you can calculate the overlap between those, basically calculating the mismatch between the different labelers. And these metrics will allow you to very quickly deselect and select images. So this way you could very easily remove all the images that they are very uncertain about, right? A lot of variation in the labeling, and then only keep those that are of high quality because all the labelers agree. So these metrics exist, are very easy to compute, but it would of course require an inexpensive way of labeling. Otherwise, you wouldn't want every image to be labeled by 3 people. But just so you know that that this is also an option.
Hamza in chat also would like to clarify that a lot of the labeling errors were made due to the difficulty of deciding what the best oil class was. And that's why, also why we mostly try to solve the general oil spill segmentation problem. So yeah, thanks for clarifying that, Hamza. All right, yeah. So we're gonna write up a report, write up some recommendations as well. We'll share some of the insights we gathered when labeling the data, and that will all come your way, Maurice, next week.
Yeah, perfect.
Furthermore, I will upload this to YouTube, and all the participants will get a peer review tomorrow, which you can fill in, and based on the peer review, we'll generate certificates. So, but yeah, I'll give a bit more explanation about that on Slack. For now, I really want to thank everyone for putting in their time and efforts into this challenge. It was a great learning experience for me as well again. And yeah, I always admire all the effort and all the sweat and tears that everyone puts in besides their normal day jobs and studies. So yeah, be aware that it's so much appreciated from our side, and thank you all for participating. That said, I want to let Maurice have some final words, and then we can round it up for today.
Yeah, all the things I wanted to say already have been said. I want to thank you again for all of the effort, and yeah, looking forward to the future.
All right, thank you very much. I'll talk to you on Slack, and for now, have a very fruitful evening.
Awesome. Thanks for the effort, guys.
Thank you very much.